Hello everyone, this is lecture 4 of ComSci 123, Stacks and Queues. A little heads up, this will be a slightly longer video than our normal ones because this video will cover 2 lecture sessions. In the first session, we will discuss stacks, queues, and decks, and in the second session, we will discuss how to implement them using arrays and linked lists. So let's start. Previously, we discussed the 2 basic data structures, which are arrays and linked lists. And if you remember, arrays are just a sequence of indexed items, whereas linked lists are a sequence of nodes that are connected via links. We also learned last time that abstract data types consists of the data structure, the set of supported operations, also known as the interface, and error conditions. So let us learn our first ADT, which is the stack. So what is the stack? It's not this one, because this is stocks, like stock exchange. It's not this one either, because this guy is just stuck to the wall. It could be this one, because the stacks, the snacks, could be thought of as a stack. Okay, and we'll see why in a while. So the stack ADT is a linear data structure that follows the last in, first out, or LIFO principle. What does this mean? So you can insert, remove, and access items only from one end, which is at the top of the stack. And if you take out items, they are taken out in the reverse order of insertion. So that's what we mean when we say last in, first out. Because the last item that you put in would be the first item that's taken out. Okay? So the stack looks something like this. You can add items to the top. You can only access items on the top as well. And you can remove items on the top of the stack as well. Okay? So only the top of the stack is accessible. Now, for the interface of the stack, or the set of methods that it supports, we have the following. Number 1, push. So when you push an item, you are adding an item to the top of the stack. Next, we have pop. In popping an item, you are removing and returning the top item of the stack. Okay? So pushing is adding, pop is removing. So you push an item on top of the stack, and you pop the item on top of the stack. So you remove it. Okay? If you don't want to remove it, you can just call top, which returns the last inserted item without removing it. This is also known as the peek method. So you only view or check or peek the top item or the last inserted item. And then you also have size, which returns the number of items in the stack, and is empty, which returns true if there are no items in the stack. So those are the 5 methods in the stack interface: push, pop, top, size, and is empty. Okay? So as an example, let's say you have an empty stack at first. When you push, so this goes all the way to, you push on top of the stack, so you have 1 currently in the stack. And then if you push another item, which is 2, 2 is pushed on top of 1. Okay? Then when you push another item, which is 3, 3 is pushed on top of 2. So now your current top item is 3. And when you pop, of course, the last item that you inserted, which is 3, would be the one that's removed first. So you pop 3 off, and now the current top would be 2 again. Now, for the errors of the stack, we have 2. First is the underflow error. And this happens when you call pop or top on an empty stack. So if you try to remove an item or get the top item on an empty stack, it will yield an error because there's nothing in the stack. There's nothing to remove or there's nothing to return. And this will happen regardless of the underlying data structure. So whether you use an array or linked list to implement your stack, underflow errors will happen. The second error is called overflow. And this happens when you push onto a full stack. Okay, so if the stack is already full and you try to add more items to it, there will be an overflow error. But this will only happen if the data structure that you use is an array, because it has a fixed capacity. So if the array is already full and you try to push more items onto the full array, then you will have a stack overflow. Okay, so this is where the term stack overflow comes from. Okay, so those are the two stack errors: underflow and overflow. Now for the applications of stack, we have the following. So page visits in the web browser are modeled using a stack so that you can return, when you click back, you go back to the last visited page, right? So if you go to page 1, page 2, page 3, if you and then you go to page 4, if you hit back, it goes back to page 3 and then back again, back to page 2, then back to page 1. So that's modeled using a stack. Same with the undo sequence in text editors. So the last action that you did is pushed onto the stack so that if you undo, the last item that you did would be removed. Okay. You can also see this in balanced parentheses and palindromes. Okay, so to check that you have like if you have parentheses, for example, you can do something like this. So this one is a balanced parenthesis, right? So you push this one onto the stack, then you push this one onto the stack as well. Then when you see the closing one, you pop this off. Then you see the closing one, you pop this off as well. And then if it's empty, then you know that it's balanced. Then you can do the same with palindromes, right? So A, B, B, A, same thing. So push A, push B. Then when you see B again, you pop it back. And then when you see A, you pop it back. So you can also use that one. Okay. Then you can also use stacks in the call stack in recursion. So the call stack is in programming languages, this is a stack wherein all your function calls are placed. So as an example, since you're familiar with the Fibonacci sequence, right? So this function is a recursive function which calls Fibonacci n. Tapos, if you have n is equal to 0, return 0. If n is equal to 1, return 1. Otherwise, return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So, how will the call stack work in this case? So, let's say that we called fib of, say, 3. So, fib 3 would be equal to fib 2 plus fib 1, right? And since we're calling fib 3 first, fib 3 will be put onto the stack. So fib 3 to be put on the stack. Now on fib 3, it triggers fib 2. So fib 2 will be called onto the stack as well. And then fib 2 is just fib 1 plus fib 0. So fib 1 will also be pushed onto the stack. But fib 1 will just return 1 here. So it returns 1. So that's removed. And then fib 0 is also pushed. So you have fib 0 pushed. But fib 0 will just return 0 here. So that's also removed, right? So let's make our stack bigger. And then after that, so you have 1 plus 0. So fib 2 is 1. And then you have fib 1. So you also call fib 1 here. But as we said, fib 1 returns 1. So this one, will return 2. So this one will be returned, and fib2 has already been taken care of earlier. And then this will become 2. So fib3 is now taken care of. So that's basically how the call stack works. When you call another function recursively, it will be added onto the stack, and then once it returns, it will be taken off of the stack. Okay, so that is your stack. Okay, so let's go to our next ADT, which is the queue. So what are queues? It's not the letter Q, okay? It's also not banana queue. Although, to be honest, one of the things that I miss the most of not being in Miagao right now is the banana queue every afternoon, right? So, but it's not this one. It's not your crush either, because your crush is not Q, but your crush is cute, right? So there's a difference. It's not this one also, right? So when you get angry at someone, you might yell pa bleep Q, right? So that's not it. That's not it either. So the queue that we refer to refers to the line, right? So a queue or a line. So the queue is a linear data structure that follows the first in, first out principle, or FIFO. Okay, so if the stack follows last in, first out, queue follows first in, first out. Okay, so like first come, first served with basis. So in the queue ADT, we can insert the items at the back of the queue, and then we can remove and access the item in front of the queue. We cannot insert in the middle, so there are no cutsies, no cutting in line. Okay, you can only insert at the back and then remove at the front, but nothing in the middle. Okay, and items are removed in the same order as insertion, so first in, first out. So if you're the first item that was uh, inserted, you'll also be the first item that will be taken out. Unlike in the stack wherein it's last in, first out. Okay, so in the queue, you add items at the back, okay, and then you remove items at the front. Okay, now for the interface of the queue, for the set of methods that it supports, we have the following. First, enqueue. So if you enqueue an item, you're adding an item to the back of the queue. Next, we have deque. If we deque an item, we are removing and returning the front item of the queue. Okay, so similar to push and pop, when you add and remove items, you also have enqueue and deque in the queue. So again, enqueue or insert happens at the back, deque happens at the front. If you don't want to remove the front item, you just want to look at it or view it, you can call front method, which returns the oldest queue item or the front item without removing it. So we call it the oldest queue item because it's the first item that was added out of the remaining items in the queue. So whichever has the longest time stayed in the queue, that will be the one that will remove first. Okay. Then of course, there's still the size, which returns the number of items in the queue, and is empty, returns true if there are no items in the queue. So similar to stack, it also has size and is empty. So those are the 5 methods in the queue interface. You have enqueue, deque, front, size, and is empty. Okay, so 5 methods in total. So if you have an empty queue at the start, you can enqueue at the back like this one. And then if you enqueue another one, you also add it to the back. So you have 1 and 2 now in your queue. And if you deque, well, 1 will be removed first because it's at the front. Okay. Now for the errors of the queue, it also has 2. So it also has underflow, which happens when you try to dequeue or call front on an empty queue. So since there's nothing to remove or nothing to return, because the queue is empty, so it will yield an error. And again, this will happen regardless of underlying data structure. So whether you use an array or a linked list to implement your queue, underflows will still happen. The other error is overflow, and this happens when you try to enqueue to a full queue. But this only happens if the data structure that you used is an array, because it has a fixed capacity. So if you enqueue to a full array queue, then it will give you an overflow error. Okay, so those are the two queue errors. Now for the applications, we have the following. So of course, your normal queues in real life or waiting lists. You also have the printing server. So if several people are asking to print something in the printer, the print server will actually enqueue all of those requests and process it in a first come first serve basis. Same thing with OS scheduler. So there are some tasks in the operating system that needs to be scheduled. So also uses first come first serve basis. And you also find this in packet forwarding in networks. So you'll probably learn more about this sa OS scheduler in your ComSci 125, then packet forwarding in networks in your ComSci 137. But all of these applications use queues. Okay, so that is queue, first in, first out. Next, let's look at the third ADT, which is Deque. Technically, it's supposed to be like 2 point something, 2.1, because it's very similar to a queue. But let's just call it our third ADT for now. So the Deque. So what is the Deque? It's not a deck like this, like the ship deck, right? It's not a deck of cards. It's not this as well. So since it's already Burr months, you'll probably hear some carolers soon singing Deck the halls and I don't know the lyrics. Fa la 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 la. Right? It's not that one as well. So what are decks? A deck is just a double-ended queue. Okay, so double-ended queue. So it's a queue-like linear data structure. And by double-ended, we mean that we could insert and delete items at both ends. So you can insert and delete at the front and at the back of the queue. So that's why it's called double-ended. Okay. Technically, you can also call it a double-ended stack because more or less it's the same. And the Deque is a richer ADT than the stack and queue ADT because the stack you can only insert and remove at the top. Sa queue, you can only insert at the back and remove at the front. But for the Deque, you can insert and remove at both ends. So it's richer. Okay, and later on, we'll see that we can even implement the stack and queue using an existing Deque implementation. So just by using Deque methods, we can implement our stack and our queue. Okay, so we can do that. So for the illustration of the Deque, you can do this. So you can insert and remove at the back. You can also insert and remove at the front. Okay, so that's the Deque ADT. For the interface, it has more methods. So starting with insert first. So you add an item to the front. Insert last adds an item to the back. And then you have remove first, which removes and returns the first item of the Deque. And remove last, well, removes and returns the last item of the Deque. You can also check the first item. So by calling first method, so return the first item without removing it. And you can do the same for the last item by calling the last method. And of course, there's still the size and is empty methods, which returns the number of items in the Deque for size and returns true if there are no items in the Deque for is empty. So in total, you have 8 methods in the Deque interface. So again, that was insert first, insert last, remove first, remove last, first, last, size, and is empty. Okay? So those are the 8 methods. And then for the errors, you still have your underflow and overflow. So underflow happens when you call remove first, remove last, first, or last on an empty deck. So basically, if you try to remove or access from an empty deck, okay, that will cause an underflow. And again, this will happen regardless of underlying data structure. So whether it's array or linked list, underflow will still happen. And then for overflow, this will happen if you insert first or insert last to a full deck if you use an array as your data structure. Okay, because an array, again, has a fixed capacity. So adding more items to a full array will cause overflow. Okay, so that is your deck or your double-ended queue. So to compare, we have sa stack, you can only add and remove and view at the top. Sa queue, you can add at the back or at the bottom, and you remove at the front. Okay, and you can also only view the front. And for double-ended queue, you can add and remove both at the front and at the back, and you can also view the front and the back items as well. But in all 3 ADTs that we discussed so far, there is no way to access the middle items. Okay, so we can only see the boundary items. So whether top, front, back, that's the only things that we can look at. But we cannot pick at the middle items. Okay, so that's it for the first part of our lecture. So we have discussed the abstract data types of stack, queues, and decks. So we discussed their interface, the methods, and the possible errors that they will yield. Okay, so now we'll go to the second part of our lecture, which is about implementations. So this is the longer part of the lecture, actually, because we will see about 6 different implementations. Okay, so 2 implementations for stack, 2 implementations for queue, and then 1 implementation for deck, and then 2 implementations for stack and queue again using deck. So I guess there's 7 different implementations that we'll see in this video. Okay, so remember that for our abstract data types, it is our responsibility as the designer to choose the data structure. So whether we'll use array or linked list to implement it, and we'll also implement the operations in the interface. Okay, so that's what we'll do in this part of the video. So we'll implement the stack, queue, and deck using arrays and linked list. And we could either use SLL or DLL. So let's start with the stack, and specifically the array-based implementation of the stack. So for array-based stack, we only need 2 properties. First is the array of objects that will hold the stack items. Okay, so this is an array of objects. And then we'll also keep track of the size, which is an integer. So this will just keep track of the size of the stack. Okay. Now for the constructor, we could create a new array-based stack like this. So array stack without any parameters. Or we could also specify the capacity of the array. So maybe we could call array stack 10. So that will create a stack using an array with capacity 10. Or if you call array stack 20, so the capacity would be 20. Now, to implement the constructor using only one method, we will do something like this in our code. So array stack capacity is equal to 10. So what this means is we will give a default value. So you can choose what value you will use, right? But in our lab exercise, I chose just capacity of 10, default value of 10. So you can call array stack like this. So that means that if you don't pass anything, the default value of 10 will be used. But you can also override the default capacity with an explicit capacity value. So if you call array stack 20, then it will create an array stack with capacity 20. Okay? So those are the two different ways that you could construct your array stack. Now for the methods, we will only implement 4 methods. We won't implement size anymore since we have a property for that one. So we're already keeping track of int size. So we don't need to create a method for that one. But we will implement isEmpty, which returns a boolean, so true or false. Top method returns an object, so the top item, but it could throw an empty stack exception. So remember, kung may underflow, it will throw this exception. And then pop will return an object as well, and it also possibly it can also possibly throw an empty stack exception, because again, if there is an underflow, if you try to pop on an empty stack, so it will throw this exception. And then finally, we'll also implement push, which doesn't return anything, so it has a void return type. If you push an item, it could throw a full stack exception, because take note, this is array based. So once the array is full and you try to push more items, it will throw a full stack exception. Okay? So for our implementation, we look something like this. So let's see. So for array-based stack, our array could be, let's say, 4 items lang, or capacity 4 lang muna. So this is index 0, 1, 2, and 3. Okay? So let's say that there are already 2 items in our stack. So if you push an item, you add it to the first empty slot. Okay, so where is the first empty slot here? That would be index 2, because this is the first empty slot. So we push the item here. So we add a new item, and then if we pop an item, we pop the last array item. So which is the last array item here? That would be index 2 with C, which contains the item that we just added, which was C, right? So if we pop, we'll remove this one. Okay, so index 2's value has been removed. Okay, and then if you look for the top item, then you just return the last array item as well. So in this case, since we've already popped the item earlier, the top item now will become B, which is on index 1. Okay, so that is your array-based stack. And then, of course, during implementation, you need to update the size property if necessary, especially when you're pushing and popping the items. Okay. Now, however, there will become a problem. There's a problem when you try to push onto a full array. For example, if there's a C here and a D here, so our stack, which will look like this. So A, B, C, D. So this is our stack, right? The top of the stack can only see D, which is this one here, the last item in the array. But if you try to push more items here, it's already full. So it will throw a full stack exception. So what will we do to counter this problem? So the solution is we will expand the array capacity once it becomes full. Okay? So if you remember in our lab exercise, what is that? Lab exercise 2, arrays and linked lists. We implemented the expand method for array, right? And we will use that exact method for this problem. So let's say that we'll expand it to twice its capacity. So the capacity right now is 4. So the new capacity would be 4 times 2, which is 8. Okay, so we'll expand this one to have a bigger capacity. So we'll now have 4, 5, 6, 7. So you now have more room to add more items. Okay, but you only expand once it's full, because it would also be wasteful to keep on expanding when it's not yet full anyway. Okay, so that is your array-based stack. Expand the array once it is full. Okay, now for the performance, okay, for the performance of the array-based stack, we have the following. So size will be constant time, because same with is empty, it's also constant time, because we have the size property that we're keeping track of. So it's fairly straightforward to implement. The top um, method will also run in constant time, because we'll just return the last item in the um, array. So we can do that with the index method, right? And then if you push, there's also constant time, because you only need to add it to the first empty slot in the array. And then sa pop, the same thing, remove the last item in the array and return it. So it's also constant time. Okay. The only thing that you need to worry probably is during push, when you need to expand, this could take more time, because you will need to expand the array. Okay. And for the memory naman, um, if C is your array capacity, so in this case, in our array stack here, the capacity is 8, right? And then let n be the number of items in the stack. So currently our n is only 4, because we only have 4 items in the stack. Okay. The memory of an array-based stack is O of C. So it's linear in terms of the array capacity, where n is less than or equal to C. So the number of items is less than the capacity. So since we are always allocating memory with the size of the capacity itself. So if you have an array of capacity 8, you always allocate 8 um, memory cells already, right? Even if you only have 4 items in the stack. So this is kind of wasteful, especially if n is very or much lesser than C. So if your number of items is much lesser than your capacity, like for example, if your capacity is 100, but you only have, let's say, 5 items in the stack, so it's very wasteful, because you are allocating 100 memory cells, but you're only using 5 of those memory cells. Okay, so because in array-based stack, you always have to allocate the memory that is dictated by the capacity. Okay, so that is the drawback of using array-based stack. It's kind of wasteful in memory. Okay, so that is array-based stack. Let's now go to SLL-based stack. Okay, so for our SLL-based stack, so we'll use a singly linked list. We'll use two properties. So first is a reference to the top node. So this will be an SLL node, or none if there is no top node yet. And then you also keep track of the size using the size property, which is an integer. Now for the constructor, you can just use it like this, SLL stack, without any parameters, because unlike in array stack, you don't need to specify any capacity, right? Because singly linked lists don't have any capacity properties. Okay, so again, you only need to use two properties: a top node, which will keep track of the topmost node of the stack, and then size. So for the methods, you still have is empty, which returns a boolean, and then your top method still returns an object, and it still throws an empty stack of exception. Same with pop, okay, returns an object, throws empty stack exception. The difference is that for your push, you don't throw full stack exception anymore, unlike in your array-based stack, because, well, SLL stack could have unlimited number of um, items, of course subject to your computer memory, but theoretically you could add as many items as you want, so it will not have a full stack exception, okay, unlike in your array stack. Okay, so for the implementation, this is how we'll do it. Okay, first we have to decide, we have to keep track of the top of the stack, right? So do we use the head of the SLL or the tail node of the SLL? Okay, so try to think about which one is better. In fact, it's easier to implement the SLL-based stack if we use the SLL's head node as the top of the stack. And I will show you why in the next slide. But for now, we'll just assume that we will use the head node as our top of the stack. Okay? So to implement this, when you push an item, we will add the node before the top node. Okay, so let me illustrate that one. So let's say we have our so this is A, let's say that this is our SLL, okay, and this is the head of the SLL, and then this is the tail of the SLL, right? So if you push an item, you add the node before the top node, and we said that the head node is also the top node, right? So if you push an item to the stack, so this is our stack, right? You add it before the top node. So you add it before this one. So let's say if we add X, you add it before the top node. So this will now become our new head node, which is also our new top node. And we'll remove this one already. Okay, so we'll add it before the top node. Now if we pop an item, we'll just remove and return the top node. So currently our top node is X, so we'll remove this one, okay, and return it. So this will now be removed, okay, and of course we also need to update the top node if necessary. So we will update the top node pointer to back to this one. So this will be our new head, which is also our top node. Okay. So the top item will, of course, that's pretty straightforward. You just return the top node's item. Okay. Whichever is pointed to by the top node, that would be the top item. Okay. So update the size and top node if necessary, especially if you're pushing and popping the items. Okay. Now, why should we use the SLL's head node as top of the stack? And why not the tail node, for example? If you remember, for SLL, it's easy to insert and delete at the front. So if this is the front, this is the head, it's easy to insert because you can just add it here and then make this the new um, new head. And if you delete, the same thing. You can also just delete the front and update the head node to be the next one. But for the back, it's only easy to insert. Like for example, if we were to insert at the back here, we could add it at the back, right? D. So this will be our new tail. But if we were to delete, remember that it takes O of n to delete at the back of the SLL. Okay? So why is that? Because if, for example, we want to delete this one, so we need to update the tail back to the previous node. But there is no way to access the previous node because we only have links to the next node. So to get this one, we have to traverse from the head and then go next, next until we reach this node to update the tail. So that takes O of n time. Remember? Okay? So it's not as straightforward to delete at the back. So, but if you do it at the front, it's easy to insert and delete. Okay? So that is why we use the head node as the top of our stack, because it's just easy to add and delete at the front. It only takes constant time. Okay? So that is the reason why we use head node as the top of our stack. Okay, for the performance of SLL-based stack, everything runs in constant time. So size is empty, top, because you only return the top node's item. Push also in constant time because you only need to add the new node before the top node. So that takes about 4 to 5 steps lang. Then for pop, the same thing. So you need to remove the top node and then you update the new top node. So that's about 5 to 6 steps as well. So constant time lang siya. Okay? Now for the memory, if n is the number of items in the stack, the memory is O of n. So it's more efficient than your array-based stack because it only consumes the memory that is proportional to the number of items in the stack. Unlike sa array-based nga, it's dependent on the capacity. And it's wasteful, especially if n is much smaller than your capacity. Okay? And it also doesn't have any overflow or capacity problems because, well, it's using a linked list. Okay? So that is SLL-based stack. Let us now go to our queue implementations. Starting with a simple implementation of a queue using an array. So we'll also use two properties here. So an array of objects and int size. So keep track of the size. And then as usual, we will still use the constructor with the default value for the capacity so that we could call it with or without the capacity parameter. Okay, just like in array stack. Now for the methods, we'll still implement is empty, which returns a boolean, front, which returns an object, and could throw an empty queue exception. So same with the queue. So it returns an object and it throws an empty queue exception because again, if you get the front item or remove the front item, if it's an empty queue, then it will return an exception or an error. And then lastly, in queue, the method doesn't return anything, so it has a void return type. And it throws full queue exception because take note, this is array based, so we have a limited capacity. Okay. So for our simple implementation, we could have our front item to always use index 0. So for example, if we have our array-based queue like this, so you have capacity 5. Okay, so say you have 3 items already in the queue. So the front item, we'll label that with F, will always be index 0. Okay, so it's pretty straightforward to get the front item. And then if you in queue, find the first empty slot to add into. So the first empty slot here would be index 3. So you add it here. So you have D there. Okay. And then if you dequeue, remove the item at the front, which is at index 0, and then you move all items forward. So what will happen is, so I'll return A, since this is the old front item. So I'll remove that one, and then I will have to move all items forward. So B will have to be moved here, C will have to be moved forward, same with D. So that our new array, or our updated array, will look something like this. So B will now be in the first slot, C, and then D. Okay, so you move all items forward. Okay, and then again, you update the size property if necessary, especially if you're in queuing and dequeuing items. Okay, you still have the same problem, which is in queuing to a full array because you are using array with a fixed capacity. So the same solution will still expand the array capacity if it becomes full. So similar to what we did in array-based stack. Okay, so I will not illustrate that one anymore. It's more or less similar to what we did in array stack anyway. Okay, so once it's full, expand so that we don't have the full queue exception. Now, for the performance of array-based queue, size and is empty will have constant time because again, we are keeping track of the size property, so it's easy to return this one. Front will also be constant time because we are always referring to index 0. In queue will also be constant time because we'll just add the item to the back of the queue, or the first empty cell. However, the deque will take O of n, which is linear time. And this is costly because we need to move the items forward. Okay, when we deque and remove the first item at index 0, we need to move all items forward. So at the worst case, let's say if the array is full, so it has n items, and if you remove the first item, you will have to move n minus 1 items forward. Okay, so that's why it takes O of n time to deque. Okay, so just like here, for example, if you deque, if you have 3 items, the one at the first index, or index 0, will be removed, and then you have to move all items forward so that index 0 will still have the front item always. Okay, so that is the first implementation of our queue using array. Okay, but since it's a little inefficient because we have to move all items forward, there is another implementation. So our second implementation using array for queue will use will still use an array of objects, but this time instead of the size property, it will keep track of 2 indices, which will be the front index and the back index. Okay, so we don't keep track of size anymore, we'll keep track of 2 indices. Okay, and we will use something called a circular array. Circular arrays will have a wrap around implementation. So what does this mean? So remember that we're keeping track of 2 indices. So what do they actually do? So front index will keep track of the front item. So for example, let me draw an example here first. So let's say we have an array of capacity 5. So it's index 0, 1, 2, 3, 4. So let's say that this array has let's say 2 items already. So the front index, I will label it with F, will refer to the front item. So in this case, the front is at index 0. Okay? The back index, on the other hand, will refer to the index with that has the next available cell for insert. Okay? So it's an empty cell which is available because it's empty, and that is where we'll add the next item when we in queue. So in this case, that would be index number 2 because it's the first empty cell where we could insert, right? Because we have two items that are occupying index 0 and 1. So index 2 is the next free cell. Okay? So our back index will refer to index 2 in this case. Okay? At the start, both would be 0 because if it's empty, for example, if 3 lang siya, 0, 1, 2, F and B would both be 0. So, in here. So, the same sila. Okay? And then, when we in queue, we will update the back index. So, what does that mean? So, let's say we in queue an item here. We in queue C. So, we in queue it to the back index. So, kung ano ang, whatever index, back index is referring to, we'll add it there. But now, we have to update back index as well because we have, remember that back index refers to an empty cell where we could add our next item to. So, the back index would be updated to index 3. Okay? So, this will be removed already. Okay? So, you update the back index on enqueue, and you do the same for front index when you dequeue. Okay, so when we dequeue, since the front is A, we'll remove this one, right? So, we'll remove this one. So, now our front index will have to be referring to B, which is in index 1. So, this will now be our new front index. Okay, so this will be removed. It will also be removed. Okay, so in this implementation, our front item is not necessarily always in index 0, unlike in our first implementation. Front item is where our front index is referring to. And front index could move along the array. Okay, so once you dequeue, you move it forward. Okay, and then when the back index reaches the end of the array, use the available cells at the front. So what does that mean? So for example, if we added D here, what will happen? So the back index will become index 4, right? And then if we add another item, let's say E here, where will back index go to? Now, back index, if we still increment it, it will fall off the array. So what we'll do is we'll wrap around and start back to the front, okay, of the array. So our back index will go all the way back here, and then this is where we'll insert our next item. Okay, so for example, when we dequeue again, for example, if we remove B, our new front will be C now, and this will be removed. This will be removed. So now you have more space at the front. Okay, so when we dequeue items, we are moving our front index forward, which leaves more room at the front for more items to be added when you reach the end of the array for the back index. Okay, so that is what we mean when we say we have a wrap-around implementation. And then the same thing for front index. Once it reaches the end, it could go back and wrap around again. Okay, so hopefully that is clear. So to do this, how will we update our front and back index? If C is our array capacity, so in this case, C is equal to 5, okay? When we in Q, we will add 1 to the back index because we're moving it forward, but we will also take the modulo of C. Why is that? So that it will wrap around. So for in the example earlier, our back index was supposed to be at 4, right? So 4, and then when we moved it um, forward, it should be at index 5 already, but index 5 does not exist in this array because it's only up to index 4. That's 4 plus 1, that's 5, but you modulo it with capacity which is 5, so that is 0. So again, modulo is remainder when you divide, right? So 5 divided by 5 is 1, remainder 0. So you go back to index 0. Okay? But this doesn't affect when you don't have a wraparound. So for example, if you're currently in 0, so 0 and then you add 1, that would be 1. 1% 5 is still 1. Okay? So that would still be 1 here if you don't have a wraparound. Okay? And then the same thing for front index. So front index plus 1, and then you take the modulo with capacity so that it could wrap around once it reaches the end of the array. Okay? So that is how you update your front and back index with wraparound. However, um, since we're not keeping track of the size property anymore, we have to compute the size using the front index and back index properties. And you have to be careful of two things, or you need to do this or compute this for two cases. First is the normal case. So this is when your front index appears before your back index. So if this is the case, you only have to compute the size for this one. Okay, so front appears before back, so that's the normal case, right? So you only need to get this size here, so in between them. But there's also a case when front is after back. So once nag-wrap around na si back, could happen like this. Sorry. So it could look something like this. Now, to get the size, you can't just get this one, right? The one in the middle. What you'll need to get is from the front all the way to the end, okay? And add that with at the start or 0 all the way up to back. Then you add these two sizes here. This one and this one. So that is your actual size because the rest here are empty. Okay, so just take note of that, that you need to compute the size because you are now keeping track of front index and back index and not the size property. Okay. However, you still have one more problem. If the front index equals back index, does that mean that it's empty or is it full? What does this mean? Okay, remember that at the start, we have, for example, size 4. If it's empty, front and back are both initialized to 0, right? So in this case, F is equal to B, right? But this is empty, okay? Now, F could also be equal to B when it becomes full. Because, for example, if you say A, B, C, so let's say this is your front, and then this is your back here, and then you added another item, let's say D, so this one will be updated to this one as well, right? So the back will be moved forward, and this time it will now equal to your front index. So in this case, F is also equal to B, but it is a full queue. right? It's not empty. So it's kind of confusing. So to do that, we will set some rules. So we will say that the queue is empty when they are equal. So only when front and back index are equal to 0, and if both of them are equal, that is when we say that it's empty. Okay, so f is equal to b only if empty. Now how about this instance when it's full? So the solution there is we don't let the array be full. Okay, so we will expand before it becomes full. So what does that mean? Going back to our example earlier, example A, B, C. So if this is our front and then this is our back, if we are to add a new item here, D, we won't add it yet, but since it's already close to being full, or it's one item before being full, so it's already, the size is already capacity minus 1 because the size is 3 and the capacity is 4. So capacity minus 1 is 3, so they're already equal. So we will already expand this one. So before it becomes full, we'll already expand it. So let's say maging 8 na siya. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, and then we'll transfer all items here. So A, B, C, and then that's when we add our new item D, so that we always have one empty cell to insert. Okay, so we never allow our array-based queue to be full. We expand it before it becomes full. Okay, so just take note of that, and you will do this in your lab number 5, I think. Okay, the second array-based implementation of the queue. Okay, so that's it. Now for the performance of this implementation, size also takes O of 1 or constant time. So even if you have to compute the size from front index and back index, it's still fairly straightforward to do it. So it only takes about 4 lines. And same with is empty, so that's also constant time. Front will also take constant time because you just refer to the index that is being pointed to by front index. Okay, so return that item. And then when you in queue, so you just add this to the back index and then you update the back index. So it also takes constant time. And then for the queue, it also takes constant time because you only need to remove the item that's being pointed to by front index, and then you update the front index. Okay, so unlike our previous implementation, we don't need to move items forward anymore. So that's why the queue only takes constant time. For memory, since it's an array-based queue, it has the same problem. So if C is the array capacity, um, and n is the number of items in the stack, our memory will always be O of C, which is based on capacity, and n could be less than or equal to C. And again, this is wasteful, especially if the number of items is way less than the array capacity. Okay, so similar issues with the array-based stack. Okay, so that is array-based queue. And now let's go to SLL-based queue. So a linked list based queue. So for this one, we will have 3 properties. So first we have the head node, which is an SLL node that refers to the front of the queue. And then we'll also keep track of the tail node, which refers to the back of the queue. So it's also an SLL node. And then we'll also keep track of the size. Okay, so 3 properties: head node, tail node, and size. And of course, at the start, if the queue is empty, head node and tail node will both be null first. Okay, since there's no nodes yet. And for the constructor, it's pretty straightforward. Again, you just have SLL queue without any parameters because unlike in your array-based queue, you don't need the capacity. For the methods, it's more or less the same. So you have is empty for that returns boolean. Front still returns an object and could throw empty queue exception. The same with the queue, so returns an object, throws empty queue exception. The only difference is that in queue does not throw a full queue exception anymore because this is linked list based. Okay, so it's not array based anymore, so it will not have the overflow problem. Now, for the implementation of our SLL-based queue, we'll do the following. So for the in queue, we will add the node after the tail node. Okay, so first, let me draw up an example. So let's say this is our queue. Let's say we only have 3 items in the queue for now. So A, B, and C. And let's say that A is our head node, which I will denote with H, and C, which is my tail node, I'll denote that with C. So this is my queue. So this is the front of the queue. Oh, so this is the front. This is the back of the queue. Okay. So again, when we in queue, we add the node after the tail node. So if we add a new item, if we in queue a new item, we'll add the item here. So let's say D. So after the tail node, right? Then of course we update the tail node to this new node. Okay. So this will be D will now be our new tail node. If we dequeue, we will remove and return the head node. So we'll remove this one, this node here, since this is the front of the queue, and we'll return it also. And then of course we need to update the head node to the next one. So this will now be our new head node. Okay, and we'll remove this node here along with its link, and B will now be our new head node, and our front will be B as well. Okay, and then of course if you want the front item, just refer to the head nodes item, which is in this case B, right? And don't forget to update the size, head node, and tail node properties if necessary, especially if you're in queuing or dequeuing items. Okay, so that is how you implement your SLL-based queue. You in queue after the tail, dequeue the head node and remove it, and then you update it to the update head node to be the next node. Okay, so in queue at the back or at the tail of the SLL, and then dequeue at the front or at the head of the SLL. So that's what we'll do. And for the performance of SLL-based queue, size and is empty, again, will take constant time because we are keeping track of the size property. Front will also take constant time because we just have to get the item in the head node, right? And then for in queue, we just have to add a new node after tail node, so that also takes about 4 steps lang. So that's also constant time. And then for the queue, that also takes constant time because you only need to remove the head node and then update the head node to the next one. Okay, so everything is in constant time for SLL-based queue. For the memory, it also uses O of n, where n is the number of items in the queue, and it doesn't have any overflow or capacity problems. Okay, so that is SLL-based queue. Finally, for our the last thing that we'll need to implement is the Deque, or the double-ended queue. So for the Deque, which do you think is better for implementation? Is it the singly linked list or the doubly linked list? If we use the singly linked list, it would be inefficient because remember that we have problems deleting at the back, right? If we delete at the back, it will take O of n time. So we will not use SLL, but instead we will use the DLL, or the doubly linked list, because all operations for the doubly linked list will take O of 1, or constant time, because it has both links to both the previous and the next nodes. Okay, since it's double-ended queue, it's only appropriate that we use the doubly linked list as well. Okay, it's more convenient. So for a DLL-based deck, we have the, three properties. We have the head guard and the tail guard, which are sentinels. So regardless of whether there are items in the deck or not, the head guard and tail guard will always exist. Okay, so since they are sentinels. So for example, um, if you recall from last time, the head guard and the tail guard, HG and TG, will always exist even if there are if the deck is empty. Okay, and then we'll also keep track of the size property. Okay, for the methods, we'll have the following. So is empty, which returns boolean. First returns an object and throws empty deck exception. Same with last. Okay, remove first returns an object and also throws empty deck exception. The same with remove last. Okay, and then insert first does not return anything, and insert last also does not return anything. And you'll notice it doesn't throw an empty or a full deck exception because we are using linked list, so there is no capacity issue. Okay, for the implementation, if you insert first, just add the node after the head guard. So it's pretty straightforward. You can do it like this. So this is your head guard, and then let's say there's already two items in the deck. So let's say this is A, this is B, then this is the tail guard TG. So we'll set up the links, here as well. Set up the links. Okay, so if this is our deck currently, if you insert at the first, just add a node after the head guard. So we have already seen this from our discussion in DLL before. So inserting after the head guard, we'll just add it here. So let's say X as our item, and then we'll update the links. So here and here, then here and here. Then of course we'll update this one. This links will be removed here. So you have inserted at the first. Okay, and then if you insert at the last, the same thing. You will need to add the node before the tail guard. So before the tail guard, you add a node here. So maybe let's say Y, right? And then update the links as well. Then this one will be updated also. So we have now effectively added a new node at the last, which is Y. Okay. If you remove first, you remove the node after the head guard, so this one. So you will remove this one and we'll update the nodes at the links. So we'll go back to that one. So back to A. So this will be removed. And then for remove last, the same thing. So this will be removed ang node before tail guard. and we have to update the links again back to this one. Okay. Then of course, if it's first, just return the node after head guard, which is this one. So the item of this one of A. And then the last is the node before tail guard, the item. So return that one. And then again, don't forget to update the size property if necessary. Now we don't need to update the head guard and tail guard because, well, they are guards. Unlike, for example, in your SLL-based queue, wherein you update the head node and tail node because they are referring to actual nodes. Here, our head guard and tail guard will remain as is. Okay, so we'll just update the links to the next or previous nodes, but we will not update the head and tail guard respectively. Okay. For the performance, everything runs in constant time. So size and is empty is constant because we have the size property. First and last is also constant because you just have to look at the next or the previous node of the head and tail guard. And then insert first and insert last. So just like I showed you earlier, it only takes about so 1, 2, 3, 4, 5, mga 5 steps, 5 to 6 steps for each one. And then the same with remove first and remove last, about 4 to 6 steps as well. Okay, so all constant time performance. Okay, and for the memory, since it's linked list based, it also uses O of n time, O of n memory, where n is the number of items in the deck, and it doesn't have overflow or capacity problems as well. Okay, so that is how you implement your deck using DLL, or doubly linked list. Now, we used the DLL implementation because in general it runs faster because all methods run in O of 1 or constant time. However, there is a slight disadvantage to using DLL, and that is it consumes more memory than SLL. Why is that? Because in DLL, you have two links to keep track of. You have the link to the previous and link to the next. So in SLL, you only have one, right? So you double the memory requirement if you use DLL. And then you also have the two extra nodes, which are the sentinels, ang head guard and tail guard, which are always there regardless of of whether the deck is empty or not. So that's extra memory if you use the DLL. Okay, but we can live with this extra memory as long as the time that it takes to run our methods will be fast, which is in constant time. Okay, so that is a example of the trade-off of time versus memory. So sometimes you have to choose implementations that run fast but has slightly more memory requirements. Okay, but if you are very limited in terms of memory, you have to use the one that is appropriate for you, but it could run slower lang because you have very limited memory. So if you cannot use DLL, you have to use SLL, but the operations will run slower because you'll have to traverse, especially if you're deleting at the back. Okay, so this is also the reason why we used SLL-based implementations earlier in our array and queue. It's because we can already run, or we can already implement our array and queue, our stacks and queues just by using SLL. So we could have used DLLs as well, but it would already be overkill, right? Because we only need a link to the next node. We don't really need a link to the previous node as well. So since we can already implement it with this SLL, it has lower memory requirements, and that is enough. And it already runs in constant time. So we chose SLL. If we chose DLL to implement our array, our stacks and queues, that would have been fine as well, but it would have more memory requirements because, as I mentioned, it has double the number of links and an extra two nodes, which are the sentinels. Okay, so just a little something to think about when you design is the trade-off between time and memory. Which one do you want to sacrifice? Okay. Okay. So finally, we said earlier that the Deque is a richer ADT than stacks and queues, and in fact, we could use the Deque to implement the stack and queue. Okay. So we'll take a look at how a Deque-based stack and a Deque-based queue will look like. So it's very straightforward. It's fairly easy. Okay, so we'll just focus on the three main methods. So the size and is empty obviously are the same, right? The methods. So for the Deque-based stack, for implementation for the implementation of the top method of stack, we'll just use last, the last method of Deque. Okay, for push, we could use insert last. Okay, and then for pop, we could remove last. So it would look like this. Um, if this is our stack and this is our Deque, so this is double-ended, right? So we could remove and insert at, at both the front and the back. Or, or I'll just call this the first and the last. So I'll just update this to L. So the first and the last. So if I want to know the top, for example, so ABC, so the top item here would just be the last item, which is C, right? If you want to push, you could insert it to the last. So you could add it here, D. So that would be pushed on top. And then if you want to pop, you remove D, you'll just remove the last item as well. Okay, so that is the Deque-based stack. For the Deque-based queue, so if you have this is our queue, this is the front, this is the back, this is the Deque, wherein you could add both sides. But here, it's one way, right? You can add at the back, you can remove at the front. This is our Deque. This is the first, this is the last. The front item here would just be the first item here. In queue, so adding here, just be inserting to the last. Okay? And if you dequeue, just remove the first, and removing the first would be dequeuing. Okay? So that is how you implement your queue using the Deque methods. Okay? So that's it for this very long video. So to review, we discussed the stack ADT, which follows the last in first out principle, the queue ADT, which follows the first in first out principle, and we also discussed the Deque, which is the double-ended queue. We also looked at the various implementations. We looked at how to implement stacks using array and SLL, how to implement queues using array and SLL as well, how to implement Deques using DLL, and how to implement stacks and queues using Deque methods. Okay, and that's it for this video. Hopefully you learned something new today, and I will see you next time.